tiny speaker on the top, and you know you get all the bass sounds, all the really low sounds coming out of the big speaker, and then a little tiny speaker up at the top, what we call our tweeter speakers. Out of those, you get all the high-pitched sounds. Have you ever wondered why you have speakers that have two speaker setups like this? Like, what would be the point of that? And would you like to know why? Because today we're talking about reflection, refraction, and diffraction of sound waves. We're going to start today by talking about reflection of sound waves. We're going to start by talking about reflection of sound waves. Now, when we talk about reflection of sound waves, you've actually heard the reflection of a sound wave tons of times before, because it sounds like this. Echo, 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 echo. Sorry, I'm way too dramatic. The reflection of a sound wave is just an echo. That's all that it is. When you hear an echo, you hear a sound that hits a wall and then, or hits a new medium and then bounces off that new medium straight back at you. That's all that a sound wave reflecting is. Reflections always happen when waves bounce off a new medium. They always occur when sound waves bounce off a new medium. Now, the first thing that you need to know about reflections is that all reflections of any wave follow the law of reflection. And the law of reflection says that the angle of incidence equals the angle of reflection. I'll draw it out right here. The law of reflection says, we'll make it a definition. The law of reflection says that the angle of incidence equals incidence. This is why I don't teach English, because I can't spell. Okay, equals the angle of reflection. Or in less wordy words, theta I equals theta R. The angle in equals the angle out. Let's draw a little picture of what we mean by this. What we mean by this is that if you take a bouncy ball and you throw a bouncy ball towards the floor like this, the angle that you send it in at is going to equal the angle that it bounces off at. It'll bounce off at an angle like this. If you take a bouncy ball and you send it straight down towards the floor like this, whoop, straight down, it'll bounce, whoop, straight back up. If you take a bouncy ball and you send it at an angle like this, it'll bounce up at an angle like this. If you take a bouncy ball and you send it in at an angle like this, it'll bounce off at an angle like this. So whatever angle that you send it in at, if you send it in at a super steep angle like this, it'll bounce off at the same angle like this. That's the law of reflection, is that the angle of incidence equals the angle of reflection. Let me show you how we label these angles. We always label these angles from a point called the normal. The normal is a point that is perpendicular here, drawing it with my light colored pencil, that is perpendicular to the surface that the object is bouncing off of. So this is my normal. My angle of incidence is defined to be right here. This is my angle of incidence. It's the angle of the bounce from the normal. This here is my angle of incidence. And this right here, my angle off, is my angle of reflection. As you can see, we define them, from this line right here, which we call the normal. And it's just a line perpendicular to the surface. That's true of sound waves too. Sound waves bouncing off surfaces, just like bouncy balls that reflect off of things, will reflect off at the same angle that you send them in at. So if you send something in at an angle, like for example, right now, if I talk at an angle relative to this thing, my sound wave will bounce off this thing at an angle as well. So that's something to keep in mind when you have any kind of reflection, be it the reflection of just a sound wave bouncing off of something, or the reflection of a light wave bouncing off of something, or the reflection of anything bouncing off of anything. That's a little bit on reflection. And now let's look at a real example. This is where I'd really love to have a giant eraser. Perhaps we should just make a new page. Let's do that. New drawing. Okay. Suppose that it was a brilliant day out at sea, and Benny the boat, you remember him, was taking a little journey. Now, here is a picture of Benny the boat in the water. Yay, Benny. Now, Benny was taking a lovely sail out at sea. It was a nice sunny day. Look at the sun in the sky. Yes, everything was looking nice and beautiful. And Benny was enjoying the scenery, looking around at the great wide expanse of ocean. And in his meanderings through the ocean, he didn't notice that coming up, approaching right in front of his face, was a giant cliff wall. Now, Benny, at this point, was really in a little bit of a tight situation here. You see, he was traveling forward at a certain velocity, and he really feared that if he continued on his way, well, he'd be destined for disaster. Here's the question. Benny, as you can see, has no eyes, and so he can't really exactly tell how far away the cliffs are. But Benny, as you can see, obviously does have ears and a voice. And so what Benny did is what any boat would do in this kind of situation. He decided that he would use his echo to figure out how far away the cliffs are and how much time he had until he had to turn around. Now, in order to do this, Benny is going to shout. He's going to shout something like, "Ah!" since he's headed towards certain doom. When he shouts something like, "Ah," that sound wave travels forward. It's going to hit the wall here. I'll draw it. Wait. Okay. His sound wave is going to travel forward, hit the wall, and then bounce back. It's going to take a certain amount of time to do this. Now, Benny takes out his special little stopwatch. Wait, let's make that. His special little stopwatch here. Sorry, colors really matter, don't they? Okay, he takes out his special little stopwatch and prepares to time the event. Now, here's what we get. We know that the speed of sound in air, I'm going to go back to black over here. Okay, we know that the speed of sound in air is 331 meters per second plus 0.6 times the temperature in degrees Celsius. And this fact will be very, very important to Benny, considering his situation. Now, here are a few things that Benny observes. First, Benny feels the air, and he feels that the temperature on that given day is a very, very pleasant, once again, he was really enjoying his day. It's a very, very pleasant 13 degrees Celsius, just slightly below room temperature, the perfect temperature for a boat. Then he finds that his echo takes exactly 0.850 seconds to get back to him, and that's the amount of time that his sound wave travels for before he hears it again. That's the amount of time between when he yells and when he hears his own echo. Benny wants to know How far away are the cliffs? Well, here's what we could do. We know an equation for the speed of sound and air, but we also know another equation for speed. It's an equation from days of old, and that's that v equals delta x over delta t. Here's what we could do. If we could solve this equation for delta x, plug in this here, this equation for the speed of sound and air and for v, then we could find delta x, which is how far the sound travels. Well, we know that delta x, in this case, is going to equal v times delta t. Plug in the speed of sound and air, and you get that this equation is going to look like 331. Wow, that's a terrible three. I just feel embarrassed by it. I'm sorry. I wish I could move on, but I simply cannot. Okay, let's try again. Doop, doop. Okay. It's going to be 331 meters per second plus 0.6 times the temperature that day in degrees Celsius times the time that it takes for him to hear his echo. And that's going to give the distance that the sound wave travels. But wait, here's something really tricky. Check it out. The sound wave travels to the cliffs and back. Benny wants to know, how far is it to the cliffs? In other words, he wants to know the distance to the cliffs, which is only half the distance that his sound wave travels, because his sound wave travels to the cliffs, then reflects back off of them and travels back to him. So the distance that Benny wants to know, delta x to the cliffs, is going to be equal to 1/2 of the distance that the sound travels. So what Benny's looking for is going to be equal to 1/2 times 331 meters per second plus 0.6 times the temperature in degrees Celsius that day times the amount of time it takes for Benny to hear his echo. Now, let's go ahead. I'm going to move myself up here. Huzzah. Okay. Now, let's go ahead and plug in some numbers and get to a final answer here. We got 1/2, 331 meters per second plus 0.6 times the temperature in degrees Celsius that day, 13 degrees Celsius, times the time, which is 0.850 seconds. Plug that into your calculator and check and see what you get. Did you get 144 meters? Wow, me too! Yay! So there's a little bit of a reflection problem for you that has to do with echoes. Now, Benny the boat uses echolocation here, and we actually use echolocation all the time, like to map the bottom of the ocean floor. We send out sounds all the way down to the bottom of the ocean. Those sounds get back to us, and we can figure out how far is the depths of the ocean. Now, we use what we call sonar to do this, which stands for sound, navigation, and ranging. We're navigating and ranging, figuring out how far away things are using sound. So we use sonar to do this, but bats also use sonar. They just don't call it sonar. They call it echolocation. Now here's a question for you. When fighter jets are trying to detect the locations of things, they don't use sonar, they use radar, which is basically the same thing as sonar, except it's using light rays. It's using light rays. Why would we use radar, light rays, for fighter jets, and why would you use sonar to measure the bottom of the ocean? Take a minute and think about it. Perhaps write down an answer. Here's the problem. Fighter jets are going crazy, crazy fast. And so if they were using the speed of sound and they were using sound to figure out how far away things are, well, by the time the sound got back to them, they would be there. And that's an issue. So they can't use sonar, they can't use sound. They have to use light instead, which goes way, way faster than a fighter jet. When we're looking at the bottom of the ocean, well, it's really dark down there. All light gets absorbed by the time you get down to the bottom. And so it makes way more sense to use sonar because the sound waves don't get absorbed by the water than to use radar because the light waves do get absorbed by the water. So we use different kinds of reflections for different things. That's a little bit on reflection of sound waves. Let's talk a little bit about refraction of sound waves. Oh gosh, well, that's not what I wanted to do. Okay, try again. Take 2. Let's talk a little bit about refraction of sound waves. Refraction, let's start with the definition here. Refraction happens when you get a bend of a wave, and I'm going to say a bend of a wave when the wave, or I should say, or part of the wave changes mediums. Refraction is a bend of a wave when the wave or part of the wave changes mediums. The best illustration I've ever heard of this is the illustration of a car driving down a road. So I'm going to show you this illustration that I saw one time that just made refraction make so much sense. Here's the idea. Suppose, yes, I'm going to use a real whiteboard now, okay? Don't freak out. This is a real life whiteboard, okay? Suppose that you had a road like this. I'm going to make my, no, this is a good side road. Okay, I feel good about this road. Let's say that you had a road like this. And let's say, I don't have a green marker. Oh, this is unfortunate. I have a pink one, that'll work just fine. Let's say that next to the road you have a nice little field of pink flowers. Oh wow, so stunningly beautiful. I was going to draw grass, but because I had a pink marker, you get flowers instead. Okay, now let's say that you had a little car that was traveling along this road, like this. And let's say that this is one of those narrow roads, one of those ones where you barely, hardly have enough space to get by. And let's say that as this car, I'll try to move this a little bit closer. Again, sorry for my janky video quality. Okay, perfect. Now let's say that this is one of those really narrow roads where like when one car passes by, the other car kind of has to like move out of the way. Let's say you had another oncoming car going this way. Well, when they cross paths, this car says, oh my gosh, you are like super in the way right now, and this is a problem. And this car, which used to have both of its tires on the road right here, all of a sudden has to dodge the situation. And one of the tires now goes into the field of flowers. What's going to happen to this car? Well, one of the tires is now in the field of flowers. The tire that's in the field of flowers can't go quite as fast as the tire that's on the road. The tire that's on the road gets to keep on going the same like road speed, but you know if you ever have like one of your tires veer off onto the side of the road, that tire can't move quite as quick. So the tire that lands in the field of flowers slows down, but the tire up here that's on the road keeps going fast. And so you have a situation that looks like this. Fast moving tire, slow moving tire. And the car turns. That's exactly what happens to any type of wave when part of the wave encounters a new medium, but the other part of the wave keeps on going. Like, for example, if you had a new medium here. Let's say up here you had air, and down here you had water. And let's say that you had a sound wave that was traveling from the water into the air like this. Well, we learned that sound travels much faster in liquids and much slower in gases. So you would have a situation where a sound wave is going like this, it's going at quite the speed, all of a sudden it gets into the air, and this part of the wave gets into the air, this part slows down here, this part of the sound wave is going to slow down, this part of the sound wave is going to keep going fast. So it's going to look something like this. As it goes, it goes, it goes, it goes, it goes, this part goes faster, this part goes slower, and the sound wave is going to end up curving that way. Do you see it? That's the idea of refraction. Refraction happens when a wave or part of a wave gets caught in the other medium, and so it either slows down or goes faster relative to the other part of the wave. And that difference in which one's going faster and which one's going slower causes the wave to bend. Back to our notes here. You actually have had plenty of real life experiences of sound waves bending. You just probably didn't know it at the time. Hopefully, you are a good Coloradan, and as a good participant in Colorado culture, you have been camping before. We have talked in this class before about how important it is to know how to roast a marshmallow. Well, it's also important to know how sound waves work when you're camping. Have you ever been camping before? And in the daytime, there's kind of lots of sounds going on, but nothing sounds all that crazy loud. And then all of a sudden at nighttime, right before it's right in the middle of the night or later in the night when the ground gets nice and cold, have you ever heard a rustling in the bushes while you're laying in your tent and you're just praying that everything will be fine and that you'll be okay, and that rustling is perhaps a bird and definitely not a bear rummaging through your snacks? Notice the next time you go camping, pay attention. Sounds sound way louder at night than they do in the day. And it's not an issue of like, well, there's just like less sounds going on. You're in the woods, you're in the wilderness. If you were near a city, we could say, well, yeah, it's just quieter. It's just quieter at night, so everything sounds louder by contrast because there are less cars driving on the road, and so then you can hear things better. But that's not true in the woods. In the woods, there are no cars that settle down during the night. It's just the woods all the time. So why do things sound so much clearer at night? Why can you hear them so much louder? Well, there's a reason. Let's take a look at a picture. Suppose that you were camping, and of course, yes, we will use amazing colors. Suppose that you're camping, and you're sitting in your little tent. Over here, it's a yellow tent, a little happy yellow tent. And it is a nice summer day. Let's not make the sun the same color as your tent. That just feels wrong. Okay, try this. Let's make it this yellow. Okay, here is the sun in the sky, shining bright. You're having the best day. Your friend who's standing outside of the tent calls to you and says, "Hey, it's time for lunch." Well, here's what happens during the day. The truth is, the reality is that the ground has a much lower specific heat capacity than the air. So the air is going to change its temperature a lot slower than the ground. The ground will change its temperature pretty rapidly. So a lot of times this ground here sits in the sun, and when the ground sits in the sun, the ground gets very, very hot during the day. And so the ground down here is very hot because it's been soaking in the sun. That means that the air right above the ground is going to be just slightly warmed because it's next to the ground and the ground is hot, so there's heat radiating off the ground and it's warming the air down here. Meanwhile, the air up here isn't quite as warm because it's further from the very hot ground that has been soaking in the light of the sun. So the air up here is slightly cooler. Here's what happens when your friend says, hey. Well, they create a sound wave, and this sound wave starts to travel forward. But now this sound wave has two mediums. Down here it has a warm medium, up here it has a cool medium. As that sound wave moves, this part of the wave that's in the warm medium moves faster than this part of the wave that's in the cool medium, and the sound wave begins to bend up and over your tent. But here's what happens in the nighttime. In the nighttime, we still have the same situation. You've got the ground underneath you. You've got your little yellow happy tent. But now in the nighttime. This time, it is no longer your friend who is outside of your tent, but a little woodland creature. Maybe little, maybe not so little. It's up for interpretation. Take a look at this animal and think what you want. Now, suppose that now it is nighttime. The sky has grown dark, the moon has risen, and this little woodland creature has begun rummaging through your snacks and is making noises that perhaps feel frightening. Here's what happens now at the nighttime. Well, now, because the ground has such a low specific heat capacity, it's going to cool down really quick. And so once the sun goes away and it's not, did I say low? Yes, good, low specific heat capacity. I hope that's what I said. Okay, it has a lower specific heat capacity, so it can change temperatures really easy. So now, at nighttime, the ground gets nice and cold because the sun isn't there warming it up anymore, which means that the air just above the ground is cooler now than it was during the day. This air up here is still warm because it hasn't quite cooled down as much as the ground has. The ground's now super cold. The air right above the ground is cooler because it's right next to the cold ground, and then the air up here is warm. Here's what happens. The little creature, call it what you want, begins to make some sounds. And when it makes some sounds, those sounds start to travel through the air. Now, they would travel straight through the air, except that this air has some different mediums to it. This bottom part is cooler, and this top part is warmer. We know that sound travels much faster in warm air. So the top part of the sound wave travels faster, the bottom part of the sound wave travels slower, and the sound wave curves downwards towards you in your tent. And so, in the summertime, when you go camping, in the daytime, the sound waves all curve up and away from you. They all curve up away from your head. In the nighttime, though, the sound waves all curve down towards you. And this is because of refraction of sound waves and because of the different mediums that sound waves travel through when you have different temperature air. There's a little bit on refraction. Our last topic for today is diffraction. Let's take a look. Once again, another drawing. Diffraction. Diffraction is also a bend of a wave, like refraction, but there's a key difference. Diffraction is a bend of a wave around a barrier or opening. Around a barrier or an opening. Let's take a look once again at our car example. Okay, perfect. Let's take a look here again. Suppose that instead of having a field of flowers off to the side, we had something just a little bit trickier. Here's my road. Here. Here's my road. And right here, off to the side of the road, is a tree. Suppose that this happened. Suppose that you had a little car that was making its way down the road, beep, 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 going down the road. And it was all completely on the road with both its tires on the road when another car started coming down the road going the opposite direction. Now this car starts coming down the road going the opposite direction, and all of a sudden this car says, wait a second, you're coming right at me and I need to move out of the way. So this car scooches off to the side. Now, when this car runs into this new barrier, a tree, it's not going to make a nice gradual bend like it did with the flowers. No, this part of the wave isn't going to slow down. It's going to completely come to a stop here when it hits the trunk of a tree. And the whole rest of the car is going to go as it wraps itself around the tree. That's the idea of diffraction. It's not that you just hit a new medium and so part of the wave slows down. It hits a new medium and part of the wave completely stops and the rest of the wave bends around. You've heard diffraction before, and you know that diffraction of sound waves is real. Because if I walked out of this room right now, and I walked around the corner, and then I said, hey, how's it going in there? You would still be able to hear me. The mic would still pick up the audio. Why? Well, because sound waves can bend around corners. What happens is the sound wave hits a corner, part of it stops, but the other part whoop, wraps around and makes it around the other side, no problem. That's diffraction. It happens when a wave runs into a barrier or into an opening and it curves around the barrier completely. Take a moment and make sure that you understand the difference between refraction and diffraction because they both involve the bending of a wave, but in different ways. Let's talk a little bit about diffraction of sound waves, especially when it comes to speakers. Here's a picture. We just talked about what happens when a wave bends around a corner, like if it hit a barrier, but let's take a look at a picture of what would happen if a wave ran into an opening. What would happen is you would have this wave that's coming in like so, drawing it kind of like ripples in a pond. When it gets to here, this part of the wave would get stuck. All of this would get stuck. This part of the wave up here would also get stuck. All of it would stop. But the part that would make it through would bend to make it through the opening. Then once it makes it through the opening, it would start to spread out again, like this, through the opening. This is what happens when you have sound coming out of a speaker. When you have sound coming out of a speaker, it bends, then makes it through the little opening, through the little speaker, and then it spreads out a little bit. Here's what you need to know is that then you get a wave that's, I'm going to use my other color. Let's go to our pencil here. That's my light pencil. You get a wave that makes a shape like this. And the angle of the bend here, whoa. Oh gosh, okay. The angle of the bend here, it bends like this, at this angle. We measure this angle from the normal between where the wave ends up, where this bend is here, and then where the opening is. This angle right here, we call theta d, the angle of diffraction, And we measure it here from this normal line. From the normal, and my pen is operating in slow motion right now. Okay, from the normal. Now here's an equation that you don't necessarily need to apply any math to, but you do need to understand. So we're not going to plug in any numbers here, but you do need to understand this equation. This equation is called the diffraction equation, and it shows how much a wave will diffract when it goes out a certain opening. The amount that it will diffract is sine of theta d, the angle of diffraction, is equal to the wavelength of that wave divided by the opening. This here is the diameter of the opening. It's how big the opening is. I'll label it on my picture here with pencil. This right here is D, the diameter of the opening. Now, see that this equation makes sense to you. This right here, sine of the angle of diffraction, is a really good measure. A way to think about it is it's a measure of how big the angle is going to be, how much it's going to spread out when it gets to the other side. Here's the idea. If you have a really, really small wavelength here, if you have a really, really small wavelength, a small wavelength would come up to this little opening here and it would say, yeah, I can fit through. And it would pass on through pretty easily without much bending. If you had a nice small wavelength here, you would have very little diffraction because that thing wouldn't really have to bend that much to make it through. But if you had a giant wavelength, if you had a big old wave and you said, okay, really big wave, why don't you go on ahead and fit through that teeny tiny opening? The wave would say, are you kidding me right now? Are you for serious? Okay, fine. And if you had a really big wave, a nice long wavelength, and you tried to cram it through a little opening, well, that thing would have to bend a lot to make it through the little space. So the size of the wavelength matters for how much that thing is going to move. The other thing that matters is the size of the opening. If you have a nice wide opening, well, something's not going to have to bend that much to make it through because the opening is enormous and anybody can pass on through. So the bigger the opening, when the size of the diameter of the opening increases, well, the diffraction, oh no, I did this bad. Doop, 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 doop. Okay. When the size of the opening increases, if you have a nice wide diameter, you need a lot less diffraction. And so the angle of diffraction is less. But if you had a teeny tiny opening and you said, hey, wave, why don't you go ahead and fit through that thing? It would say, are you for serious right now? That thing is so small. I'm going to have to bend myself like crazy to get through. And it would have to bend like crazy to get through. So you get way more diffraction. Hopefully, this equation makes some amount of sense to you. But now, let's talk about it with sound. Specifically with speakers. You wonder why speakers have those 2-speaker setup? You got the big speaker on the bottom for the low pitch sounds. Then you got the small speaker on the top for the high pitch sounds. We'll see if this makes sense to you. Let's talk about sound waves. Here are a few things that you need to recognize about sound waves. The first thing that you need to recognize about sound waves is that high frequency waves, which, by the way, if a wave has a high frequency wave is something that looks like this. Beep, 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 beep. Lots of waves in a short amount of time. Hey, check the wavelength on one of those things. Teeny tiny wavelength. So high frequency sounds, which also happen to be low wavelength sounds, or very small wavelength sounds, they naturally diffract less. Sorry, I gotta wait for my pen to catch up. They naturally diffract less because they're already small, and so they can make it through the opening easily. Low frequency sounds, which, by the way, look way more like this. Check one of these wavelengths. It's enormous. A low frequency sound where you're seeing few waves per second, so those waves are way spread out. You've got a nice big wavelength. They naturally diffract more because they have to bend a lot to get through the opening. So if you sent a high frequency sound and a low frequency sound through the same opening, the low frequency sound would naturally spread out more and would go all over the room. But the high frequency sound would not diffract that much naturally, and so it would mostly stay in kind of like one line through the center of the room. Here's the problem. If you're listening to music, you want to hear your high frequencies everywhere in the room, and you also want to hear your low frequencies everywhere in the room. You don't want to have certain patches in the room where you can hear the low frequencies really well, but you can't hear the high frequencies. You also don't want to have patches in the room where you're like, whoa, those high frequencies are really loud, but like only right in this patch. It's like they're not going anywhere else. They're only here. That's not the situation that you want to have. If you're listening to music, you want to hear the high frequency sounds all over the room and the low frequency sounds all over the room. You want them evenly balanced. So here's what we do. We make a double speaker. One speaker, the top speaker normally, has a small opening, and the bottom part of the speaker has a nice big opening here, like this. When the sound waves come out, we send all of the high frequency sound waves through this one. Oh, I kind of wanted a pen, actually. That is embarrassing. Not chalk. Whoever wants to write in chalk on one of these situations, I just don't know. Chalk is like all kinds of inconvenient. Okay. We send all of the high frequency sounds or the low frequency sound, the high frequency or the small wavelength sounds through the top speaker. And then we send all of the low frequency sounds or the big wavelength sounds through the bottom speaker, through the bigger speaker. That means in this equation, oh my, it's taking so slowly to write everything that I need to write. Okay. Let's write this for both situations. For your high frequency sounds, your wavelength is really small. So in order to make those sounds diffract more, we make the diameter really small. And by making the diameter really small, we make those sounds that naturally wouldn't diffract very much, we make them diffract more. But on the other hand, here you have really big wavelengths. Those big wavelengths would naturally diffract a lot. So in order to make them diffract less and spread out less, we give them a really big diameter to go through. And that counteracts the fact that they would spread out so much all over the room. And so then when you have the low frequency sounds coming from the big speaker and the high frequency sounds coming from the small speaker, the sounds spread out evenly, and you can hear the low frequency sounds everywhere in the room and the high frequency sounds everywhere in the room. Doesn't that just seem great? Oh, yes, we're so smart, aren't we? Well, folks, that's a little bit about reflection, refraction, and diffraction of sound waves. Make sure that you understand the definitions of each of those three terms and how they're all different from each other, and also how they could each be applied to specific real-world situations. I hope you have a wonderful rest of your day, and I'll see you all later, good people. Bye.